Hello and welcome to Studying with Chris, where I try my best to explain topics to help both you and me understand concepts. Today we'll just be talking about properties of quadratic functions. So, we talked about quadratic functions from factoring and the quadratic formula, but what are some attributes to the quadratic functions themselves? So, right now, we're on Desmos, and I'll show you some things that you can um, try yourself or just experiment with on Desmos. So, right over here, I'll do y equals x squared. Now, this is an example of a quadratic function. So, as you can see, my equation has a degree of 2, and it takes the shape of a parabola. So this almost like curve is known as a parabola. And there are many types of quadratic equations. I can do y equals negative x squared, and it's quite similar, just flip down. I can do y equals 2x squared minus 4 plus 3x. I can do many different shapes, and there are many types of equations for um, quadratic functions. Now, for now, I wanted to um, talk about the solutions. So when you're solving for a the solution to a quadratic function, might notice that it's always equal to 0. So you would have, say, x squared plus 4x minus 3 is equal to 0. Now, that's the case because when it's equal to 0, it's talking about the height. So as you can see here, on the y-axis, the height is equal to 0, and there's only one intersect here. That means for y equals to x squared, there's only one solution to this answer. So that basically means when y equals to 0, x only has one solution. Now let's see if we have x squared minus 1. Now you can see when y equals to 0, there are two solutions now, which happen to be plus 1 and minus 1. So whenever we talk about the zeros for a equation or the solutions, we always mean whenever the quadratic function is at a height of y equals 0. So in this case, there are two intercepts, so there would be two answers. Now, for quadratic functions by themselves, at most, you will only have two answers. So you can have no solutions, which is when it never intersects with the x-axis. So if I say x squared plus 1, as you can see, there's no intersection, which means there's no answers. There can be exactly one solution, as you can see here, where there's one point intersecting, or there can be two, as I mentioned before. When you're dealing with other functions in addition to quadratic functions like reciprocals or absolute values, then it becomes a little different. But quadratic functions by themselves will either have 0, 1, or 2 solutions. Now, alright, so another property of quadratic functions is the coefficient. So as we mentioned before, in general form, our equation takes the form of ax squared plus bx plus c equals to y. So in this case, our a term is known as it's kind of like our coefficient, but it's also kind of the variable that determines our stretch and compression. Now, what does that mean? So as you can see here in our parent function up here, we have y equals to ax squared. Now, as we change a, try to see what happens. So if I increase a, you can kind of see how it gets thinner and thinner. So this is just known as a vertical stretch. So if you think about like pulling these ends and pulling it closer and closer together, it's kind of like stretching the function out. Now if I go, I'll change this really quickly. If I go to, say, 0 with a step of 0.1, okay, so I'm at 1 right now. Now, if I start making it go between 0 and 1, kind of see how it gets wider and wider. So this is known as a compression, which if you think about like squishing the quadratic equation flat, so then it becomes um, basically a flat line when a is equal to 0. And then let's change our domain for this again. Now, we're at 1 right now. So then try to notice as a is equal to a positive number, so in this case positive 1, it opens up. And right now it's still positive, and when it's at 0, it's a flat line. Now when we go negative, it curves downwards. And as you increase the magnitude of this such that it goes above 1, above, yeah, above the magnitude of 1, then it starts stretching again. And once the magnitude of it is between 1 and 0, it starts compressing. So, if you're learning this in Math 20-1 for the Alberta curriculum, I don't think there's too much about stretching compression aside from theory based, but it's helpful to know what the shapes would look like and how it's dependent relative to A. Now, if I set this to A equals to 1, now, in the parabola, there's many key features to it to know how to identify it or how to find solutions for it. So as you can see here, I mentioned the intersections and solutions. So those are known as your zeros. Those become incredibly helpful in the next unit as well for inequalities. So for our graph here, right now, you might be able to know that there's always one point. So like kind of like a maximum or a minimum. This is known as our vertex. So I'll take this out of the way. So if I change our equation here, as you can see, there's this one point at the very bottom that's 0, 0. And there's no point that goes kind of below it. And if I change this equation to something else, it's 2, for example, you can see here, there's another point that kind of stops the it's like a restriction for the y value of the parabola. So this is known as the vertex, as I mentioned before, and it can also kind of be commonly known as a maximum or a minimum. So for instance, in this case, if I have negative x squared plus 2, I have a maximum value for my y. So my y value can never be 3 because the graph never reaches that point. However, it can be anything below a y value of 2 because it just goes on infinitely. So as you might be able to also tell that a maximum or minimum is very dependent on our a value. So if I put a back here again, as you can see, if it's positive, I have a minimum value. So this is the lowest value it can be and it can't go lower. But as soon as I make a negative, it turns into a maximum value. So there can be no value that's higher. Now, what's also pretty cool is the vertex, the x value for the vertex, so in this case it's 0, this is known as our axis of symmetry. So it's always going to be the x value of the vertex. So in this case, as you can see, the x value is 0, and 0 here, if we say x is equal to 0, and I'll change the color of this. There we go. Now, as you can see, there's this dotted line here, and what's really cool is, if you haven't been able to notice it, it's a perfect mirror over. So when the value of here is negative 5 and it's 5, it's the exact same y value. So that's why it's called the axis of symmetry, because it's almost like flipping this entire half of the graph to the other side. Now that's really helpful when plotting points, because if you have a linear function, you have to calculate the y value for every x value. But for a quadratic function, if you calculate one x value, you already automatically know what the other y value is going to be relative to the axis of symmetry. Now, it's not always going to be 0 if I ever translate my graph over. So I'm going to do something else here. If I translate my graph over to the left or right, or just anywhere along the x-axis, you can see how x equals 0 is no longer a axis of symmetry that can satisfy this parabola. So then once again, I need to look at my vertex. In this case, I see it's -3. So I say x is equal to -3. Now I have an axis of symmetry, and any point that's, say, 2 or 3 units here. So for example, roughly here, it's -6 and 9. So I know if relative to this it's -6, so 3 units to the other side will also be 9, right? So that's a really cool thing for axis of symmetry, and that can help with many theory problems. The vertex can also be a very helpful point for figuring out the domain or range. So as I mentioned before, there's restrictions depending on if it's a minimum or maximum. So if my a value in this case is negative, right, I can say my domain, so the x restrictions, well, there's no x restriction because this will continue on infinitely, and it'll eventually travel across the entire um, x-axis. So I can say that for my restrictions for the x-axis, or the x values, would be x belongs to real, but then my restriction for my um, y values, so my range, would be that x has to be less than or equal to 0, since my vertex has a y value of 0. Now this can always change, so if I go here, and I can say that my x coordinate will stay the same, but then let's say I do this. Now I can see that my vertex is at -2, and this is a minimum, so there's no value that's lower than that. So I can say that for my range, I can say that y has to be greater than or equal to -2. Other than that, this is really it. These are the main components to parabolas and quadratic functions that I know to the best of my ability. If you have any questions or you require any further explanation, feel free to let me know. Otherwise, thank you for studying with me.